why 1427A is called A can put it in the chat. Okay, next speaker is Timur. We're going to talk about UCDs.
Okay, great. I will share my screen now in a second. Now you must be able to see it, right?
No. Yeah, no.
Okay. Now in full screen.
Yeah.
Okay, so after hearing a lot about dwarf galaxies in Fornax, I'm going to talk about a different type of objects in Fornax. They can be galaxies, they can not be galaxies. Actually, it's very complicated at the moment. They're called ultra-compact dwarf galaxies. The term galaxy still exists, but this is something historical. We'll talk about it later. This work is a big work. Rainier, well, he is my main advisor. He's also helping for this work. Joachim and all the collaborators from FTS are also involved. Then, so this is something I started in the beginning of my PhD and still ongoing, and I hope that 2020 be the last year I'm working on this. So I'm going to give a very brief introduction on these objects. Here I put all sort of astronomical objects that we are interested in this size spectrum. We have giant galaxies of order of 10 kiloparsec of the sizes. We have dwarf galaxies, which are 10 times more or less smaller. And then we have some particular objects like M32. They're not many of them known. M32 is one of the most famous examples of these objects. These objects are smaller than dwarf galaxies, and they're called compact dwarf galaxies. And then at the end of this spectrum, we have global clusters that are even 10 or 100 times more smaller than these compact dwarf galaxies. So this trend in size, you can also translate it to luminosity or mass. Just very general trend. It doesn't mean that it works for everything, but more or less things are, when they're bigger, they're brighter, and they're also more massive, something very general. Then we can put a line here. We can see a separation between the different kind of objects. We can put some of them on the right, some on the left, and everything on the right, we can sort of call them galaxies. They have, as we know, they have a dark matter halo or some sort of dark matter exists in them. They also host a supermassive black hole in the center. And the objects on the other side, like global clusters, they don't have any dark matter as far as we know, and they don't have a supermassive black hole. So this is a classical definition of galaxies and star clusters. But then in Fornax Cluster, which actually we are studying in FDS, in sundial, about 20 years ago, people found some objects in the redshift of the cluster, which means that these objects are in the cluster. But the sizes of these objects was smaller than what they expect for galaxies. And they were smaller than these compact dwarf galaxies that I showed, like M32 like galaxies. And people at that time, they came up with the name of ultra compact dwarf galaxies. They also thought they're just they are galaxies, but just even more compact than compact dwarfs. This puts UCDs here, and then when you follow the same category, when you follow the same definition we defined before, then now there is a problem. Are they galaxy? Are they star cluster? Or what we should say? Now there is no clear separation between these two type of objects. So then, in general, there are different, after let's say 2 decades, people have two main ideas about how these objects are formed. And one idea, which is more interesting here for us, is that they're actually originated from galaxies. Galaxies interact with each other, crazy things happen in galaxy clusters, and nucleated dwarf galaxy, like this galaxy on the bottom of this frame, can interact with other galaxies, bigger galaxies, due to gravitational tidal forces, loses the stars in the outskirts, and what remains is the nucleus, which is gravitationally strong enough to hold itself. So this nucleus lives there what you see, what we see at least in the Fornax cluster, it's just it's not a galaxy, actually a remnant of a nuclear dwarf galaxy. So this type of objects are interesting for us because when we have, if we find UCDs, we can say, okay, these objects, they were before, they were nuclear dwarf galaxy, they were a dwarf galaxy. So we somehow can understand the rate of destruction of galaxies, and people who study the luminosity function in the galaxy clusters wants to find out how luminosity function changes from environment or different times. They can recover using this rate of destruction, they can recover the true shape of luminosity function before this galaxy being destroyed. Also, since it has been discovered that at least in 5 cases, 5 big, bright and with high signal to noise ratio, bright ones that you can get high signal to noise ratio observations out of them, people found supermassive black holes, not the one that I showed here, but just to give the idea that there is a black hole. Finding these objects and measuring black holes is also important to derive the mass distribution of black holes in the universe and all the studies about formation of supermassive black holes. And also, as I mentioned before, finding these objects and studying was important to understand the role of environment that in many of the FDA studies, we also try to investigate. Okay, then I go to Fornax Cluster again. So Fornax Cluster was the place that these objects were found for the first time. And till now, we have more or less 60 of these objects spectroscopically identified. So it means that we have redshift for them. We have a sort of distance for these objects. We can say, yes, they are in the Fornax cluster. They are there. But then when you look at the Fornax cluster, all these red points are the confirmed UCDs that are found before. Everything is inside this circle, which is more or less half of the virial radius of the cluster. But what about rest of the cluster up to this like black circle, that indicates the virial radius of the cluster? That was the question we asked, that we wanted to find these objects far from the core of the cluster because we're curious. We want to see what we will find. So how we find this, I mentioned before that is confirmation of UCD needs some spectroscopy, but also we can do photometric studies. And as I will show you later, this study for some reason is better than the previous works that try to find this sort of objects in low redshift. So the way that we find this object is mainly based on their colors. We have, for example, two colors like UI and I minus K. And also we know that these objects are small, so we can constrain their sizes. Big objects are not UCD, so we can just throw them away. We have some objects that we know that they are UCDs or stars or galaxies, and I showed them, for example, in this plot as an example in color, and all the other objects that we don't know about them, and they are in gray. And the UCDs are in a region, defined a region, and we just select everything there. Every gray point that is around these red points, it can be a UCD candidate for us. Then we go further. We have for example, the plot that I showed was just based on 2 colors, but we have more colors. We have 5 independent colors based on a data set, optical and near infrared observations, FDS for optical, and some other archival data of ESO for near infrared. But the question is that, so I mentioned before that what is better than before, but why? And why we couldn't find these objects before? Well, we could, but let's say when you just using optical data, like this plot on top, it's like 2 optical colors, UI, GI, you can see that red points that are UCDs are really on top of the stars and galaxies. So if you select some UCDs, so if you select objects that are in the red region, then you probably also select lots of stars and also galaxies. And this is it gives you a sample of candidates, but the sample is very contaminated by other objects. But then when you use near infrared that we have in this work, you see that you can separate like this plot here on the bottom I showed, you can separate the UCDs from stars and galaxies a bit, well, somehow more, and then you will have a more clear sample at the end. So that's the whole thing. We have colors of objects. We look at the colors in different parameter, in different colored spaces, and we select UCDs. Okay, I go to the down of the road and talk about what we find. What we found is around 220 UCD candidates in a cluster, objects that don't have any spectroscopic data, any radial velocity, any redshift. However, based on all sort of objects that we have there, we can estimate how many false positives we should expect. We have a rate of false positives. We have also like some number of objects in that region of the sky, and we can estimate the rate of false positives. And this gives us that among these 220, more or less 70 of these objects can be true UCDs, and the rest are true or false positives. That's why we focus on the most likely objects. We have probabilities that we measured for these objects to be a UCD. We select the most likely ones, and it ends up with we end up with 45 UCD candidates. It is smaller than the rate that we expect to be true, which means that this is a very how to say, we can be confident about the nature of these objects. We also did some sort of tests like, okay, how many of these objects we can find, how many of objects that were found in other surveys have been recovered. For example, in ACS surveys of Fornax Cluster, where it doesn't do a spectroscopy, but it has a very high resolution imaging, and they can find objects that are UCD based on the sizes. They found, we could find 85% of the UCDs in that catalog, which the fraction that we miss is actually because of the source extraction, and it is because of our data set that doesn't let us to actually look at that region of the data. It is somehow not a nice region of our data. We cannot use it. Then another small test, we have Gaia stars. We have parallaxes. We can say which objects are stars. And interestingly, none of our objects are actually in the Gaia as a star, in a star list of Gaia, let's say based on some parallaxes. They don't have any parallax. And at the end, we also compared the result with another work of FTS that found UCDs in Fornax based on optical data. And this, just adding near infrared, shows that 90% of the optically selected UCDs can be just stars. And we already can make our sample cleaner based on using near infrared. Then somehow my last slide that I represent some of our findings. And so this work is about finding these objects, and we want to study more, but to study better, first we should do a follow-up spectroscopy. This is something for future, to be sure that these objects are members for 100%. And also, it's really hard to understand our result because we have simulations of UCDs in the whole cluster are lacking of good quality, or even we don't have that many simulations to help us to interpret our results. What we do, we just look at the cluster core, something I define as everything inside half the virial radius, and cluster outskirts, something I define everything within the virial radius and further than half the virial radius. And we see that 30% of the UCDs in total are in the outskirts. And also, assuming that the objects that we found in the center, in the core of the cluster is where it's studied a lot before with the spectroscopy, assuming that those objects are actually still false positives, which we doubted, but let's say they're false positives, we can somehow estimate even we can estimate a lower number for the total UCDs that we see in outskirts. And the number that we derive is a good number here that simulations in future should be able to reproduce. Okay, then another interesting thing was that we look at UCDs that we found, and some of them are around galaxies. let's say for big galaxies in the Fornax cluster that I showed with blue and green, the circles around them, it shows 200 kiloparsecs from each galaxy. And let's say in a very simple view, objects inside the circles can be associated to these galaxies. This is the way, this is because bigger galaxies will, the gravitational potential of big galaxies can actually make UCDs out of nucleated dwarfs. So that's why that's the place that we usually find them. But interestingly, half of the objects that we found are not associated with any galaxy in that sense. So they can be intra-cluster UCDs or some sort of free-floating. We should note that everything is in a projection, in the projected view, and things in 3D can be totally different. But that's what we can do here. Okay, and we also did comparison with Virgo and Fornax. Virgo result is from another paper, and we just took the catalog. They don't study the cluster that much. And something we did led us to this finding that Fornax looks to have more UCDs in the outskirts compared to Virgo, at least Virgo A with the M87 in the center, which is the main part of the cluster. Okay, so I leave my summaries here, and I would be happy to answer your questions if there is any. Thank you.
Yes, questions.
I have a question connected to the original selection of the galaxy. So when you saw at the beginning of your talk, you saw the color map showing all the galaxies and all the stars and so forth. Did you make any, that one. Did you make any pre-selection based on size of these objects? Just to identify.
Yeah, actually, that's so. Before this plot that I actually showed here, everything is pre-selected based on sizes. So we have an upper limit, and everything larger than that size is excluded. And objects that I show, at least for example, galaxies here are smaller galaxies. Stars are just point sources, so they're all selected.
Okay.
Yeah.
So my other question is, you are using color maps to separate or to select the potential candidates. I was wondering, why do you not use all the information that you have? I mean, why don't you base your selection on a spectral energy distribution of the confirmed ultracompact dwarf?
So you mean okay? So what does a CD can give us? Like it's also based on some magnitudes and colors that we're already using it. So we are using that information in other ways, right?
Yeah, but if you can use all the information together, probably it has a larger potential, no, to segregate galaxies than just based on a couple of colors, right? Particularly when most of the colors are just combination of each other. For example, you combine R minus I versus U minus I, things like that.
Well, yes. So we have this first of all, this that I show here is something that I made before. Now we have a different set of colors. That one point to keep in mind. Another one is that at the end I'm using 5 colors, so all 5 are independent. There is nothing repeated. Like you cannot produce let's say you cannot reproduce one from the other ones. So there is no repetition. But I don't know if you fit a CD on a galaxy on an object. Maybe you introduce more uncertainty, and still it's the same information. I don't see that you add more information somehow.
I think it's the same.
Can I say one more thing? So I guess that you also could add another 2 filters here. If you use the decal survey, do you know that survey from the telescope Blanco in the southern hemisphere?
Yeah.
They go very deep, so there's a similar depth to this one probably, and you can include the G band and the Z band. And so then in the end you would have like 7 filters, and that probably will make you very nice SED for fitting these objects.
In G bands, is it different than G that we have here?
Sorry. So you have the G band, the Z band. I mean.
Z band. Okay. Yeah.
And the R band as well. So you have it always. Okay. So yeah, Z band would be included.
I think. Well, if I knew this a bit earlier, I could probably use that as well. How I don't think it will be very helpful. It's not going to check. Things going to be very similar at the end because we have J and K, and it already has everything that we want from the other side of the spectrum. Then it's a good idea to include it if something we want to do in the future. How deep is it? Maybe we can do it for global clusters at some point.
My question here is how trustable is it? Well, I guess the observations say it, but what do we so how do you get 40, 50 of these UCDs in the outer parts of the Virgo cluster? I mean, that to me, I really don't get how you can make these galaxies there if they're formed by stripping the outer regions, etc. Does anyone have any ideas about this?
You are saying Virgo?
No, sorry, Fornax. I'm not there.
Okay. Well, I have my own opinions here also, but then let's wait.
Sven or someone like that can give an opinion or whatever.
Yeah.
In Fornax, everything is so centrally concentrated that you really need to bring in a galaxy very close to the center to get it into a high density region to get it stripped. So if you find them now in the outskirts, then it could be a backsplash population. They've been through the center, but are now on their way out again. You don't observe them where it's happening necessarily, right?
No.
Yeah.
Yeah.
But immediately when you're beyond a few hundred kiloparsec away from the cluster center in Fornax, you might as well be in the field.
I mean, is it easy? Would it be easy to make, say, back of the envelope calculations to estimate how many of them there are?
Is that a question to me? Or?
That's a question to you. Yeah, I mean, would it be possible to make some calculations to see how many you would see?
That's a difficult question.
Yeah, difficult. Okay, well. Okay.
But then you need to know the progenitors more or less.
Yeah, I mean, but
you need to know the progenitor population and what fraction of that progenitor population is actually brought very close into the center and transformed into UCDs.
Yeah.
It will be a pretty small fraction because you really need to get to the center. But you said that you had opinions, so Timur.
Well, I don't have, okay, I have opinions about how they can be more than, so for example, some of them can just be pre-processed somewhere else and involved with cluster. And some of them, I don't want to say it officially, but I really like the idea of the ones that formed in earlier times in the universe, like primordial UCDs, something like this. And they can be everywhere. So, but then about some calculations that how many UCDs in general we can expect there, because we can expect some, but what is this number? That is, I don't know. That thing, I think it needs actually a different work, like someone see it and based on the population of galaxies that exists already in Fornax environment, try to calculate things and maybe use some sort of simulation that already exists. So it is quite huge work if someone wants to give some number. Agree?
Agree.
Okay. Anyone else? No. Have we figured out? Have we figured out why galaxies are called 1427A or 37A?
Okay, I'm reading here.
So my guess was, since it's fainter than most of the
Hmm.
galaxies that were awarded an NGC number, is that it was a late addition.
Yeah, maybe.
But then again, I don't see why it was linked with NGC 1427, which is an elliptical and which is quite far away.
Yeah,
It's
it's
actually it's much closer to NGC 1404 or something like that. I mean,
But then NGC catalog is based on right ascension.
yeah, the numbering is based on right ascension, so
Maybe
but
the
that also
inflation
doesn't
doesn't
make
matter.
sense. If you look at the right ascensions, then it also doesn't make sense.
Ah, okay.
it was based at the right ascension at a certain time, but I guess even that doesn't make sense. Even with proper motion, because proper motions are basically nothing.
Yeah, no,
No, that makes a difference. I mean, because you have parallax, you have the equinox changes from 1900, 1950, etc. So the coordinate system changes. Like a galaxy like 7814 is at right ascension
okay.
0, 0, 1, etc., and not 24.
So you mean that the NGC numbers are based on an old right ascension, and NGC 1427A is based on a newer